The purpose of this lab is to understand loop rule, understand current conservation, which includes charge conservation and definition of steady state, as well as predict behaviors of circuits in different situations. Our results, we saw that online circuit model matched our predictions made by formulas. The fundamental physics principles at hand would be conservation of charge, Kirchhoff's law, which includes node rule and loop rule, steady state circuits, and Ohm's law. In the experiment, we have our circuit, which includes two 1.5 volt batteries, 2 ammeters, a 47 ohm resistor, and a 100 ohm resistor. And we made the assumption that there is no resistance in the wire or the ammeter. We predicted that the first and second ammeter in the circuit would measure the same current due to the node rule. And in our simulation on the right, you can see that that held true. And when we measured the current backwards with the ammeter, it was negative, but the same magnitude. When we replaced one ammeter with a voltmeter, we saw that the voltage was 3 volts, but the current dropped down to 0 amps. And the reason for this is that the voltmeter closes the circuit to measure voltage, but it prevents further current from moving along the circuit. And when the circuit is open, there's no current, and the potential difference stays constant. And on the right, we have the math that we saw that the math we did for the current matches the one we saw in the simulation. When we measured voltage across the circuit, we saw that there was 3 volts across the 2 batteries, which is what is expected. And then at the 47 ohm resistor, it was negative 0.96 volts. And at the 100 ohm resistor, it was negative 2.04 volts. And on the left is the graph showing the increase and decrease of the voltage as you move along the circuit. And adding the voltmeter doesn't alter this current since this resistance is so high that any effect it has on the circuit is negligible. And we also noted that due to the loop rule and the round trip potential would be 0. Now when we put our circuit in parallel, we saw that the current actually went up. And that is because the same amount of current is flowing through the wires, but some of it is going through the ammeter and some of it is going to the resistor. So the resistor isn't resisting as much current as it was in series, and so the total current goes up. And we also calculate the resistance in each, in the 47 ohm resistor and the 100 ohm resistor. We got 48 ohms and 102 ohms, and those voltages are what we measured in the previous slide. And the wire and ammeter, since there's 0 volts in it, the resistance is also 0. There's less current, remember that. In the RC circuit, we saw that as you close the circuit, the capacitor charges up. And if you were to only have the capacitor in the light bulb, the capacitor does discharge into the light bulb, but once that charge is gone, the light bulb dims back down. And the light bulb, when with the battery and capacitor, is only lit up until the capacitor is fully charged. So once it's fully charged, the light bulb dims back down. For the 100 ohm light bulb, we saw that it took 4.74 seconds to charge, 7.94 seconds to discharge, and the 20 ohm bulb, it took 6.44 seconds to charge and 10.28 seconds to discharge. So the higher the resistance in the light bulb, it does take longer to charge, but it also takes longer to discharge. And in the last part, we saw the time it took for the capacitor to charge and discharge, and we were trying to find the time at which the voltage difference has dropped to 1 over E, which is the time constant. And on the graph, we have time and then the natural log of the change in voltage divided by the change in initial voltage of the capacitor. And the slope was negative 0.1664, and we saw that R observed is 6 seconds, and we expected 6 seconds based off this math. Now, what if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? Well, with real life components, not everything is ideal, so the resistance in the resistors would be slightly higher or lower than what we expected. Most resistors have a tolerance of 1 to 2%, and in real life, ammeters and wires do have resistance. So the current we calculated in the simulator, which was 0.02, is higher than what would be in real life since it doesn't account for the additional resistance. And then, what if you were doing this lab in real life and using a real battery to charge a capacitor with no resistor in the circuit? How quickly would our model practice the capacitor to reach full charge? What we measured, again, didn't include any resistance in the wires, but in real life it would. So the capacitor would charge and discharge slightly slower than what we expected. And our conclusions are the capacitor holds charge and discharge over time. Parallel circuits increase current in a circuit. Round trip voltage is 0 volts, and possibility of error, timing of discharge of capacitor, since we measured that with the stopwatch, and the wire and ammeter carry some resistance that we didn't account for. Yeah.